recording. There we go. All right. So we were left off at bicyclic compounds. So we finished compounds that are linear and have cyclic side chains. But when we're talking about bicyclic compounds, these are compounds that have two rings fused together. Like you can see here, we have a six-membered ring. 1, 2, 3, 4, 5, 6. But then there's also a five-membered ring in it, right? 1, 2, 3, 4, 5, like that. So this is the same thing as looking at it like this. You could say again, 1, 2, 3, 4, 5, 6. And then you could also say 1, 2, 3, 4, 5, whatever. Anyhow, I'll teach you how to number it properly in just a couple of seconds. So we'll skip all these so they're consistent. Anyhow, so to name a bicyclic compound, we include the prefix bicyclo in front of the parent name. So if I can show you very quickly how you would name this compound here, and again, this compound and this compound are identical, but the way you do it is you start on one of the what we call a bridgehead carbon, and the bridgehead carbons are the ones where the bridge is, and you can see that this is the bridge here. Anyhow, it's where the rings are fused together essentially. So because you can't have a bridge that has no carbons in it, and I'll show you an example of that. But these are what we call the bridgehead carbons. You start numbering at one of those in the way that you give the first substituent the lowest possible number. There's no substituents on here, so we don't have to worry about that. So we start by numbering the longest ring, or the largest ring. So 1, 2, 3, 4, 5, 6. Okay, and then we have 7. So we'll put carbon number 7 up here. So the way you would name this is you would say bicyclo, and then you put an open square bracket and a closed square bracket. Then inside the square brackets, you put 3 numbers, which are the lengths of the bridges. So those 2 highlighted carbons, those are the bridgehead carbons. So one of the bridges, okay, has 2 carbons. So we put a 2 dot. Another one of the bridges has 2 carbons. So we'll put 2 dot. And then the last bridge has only 1 carbon. So 2, 2, 1. And then if you tally up the total number of carbons, which is 7, we say it's a bicycloheptane. So we would finish this out with heptane, like that. So bicyclo 2,2,1 heptane. Now, if that doesn't make sense, let me show you here on this slide. Okay, so the 2 carbons where the rings are fused, we call those the bridgehead carbons. Okay, there are 3 paths. Okay, I can take this path, I could take this path, or I could take this path, right? 3 paths around those bridgeheads. But what I do is I start with the longest chain and go to the shortest, or the longest bridge and go to the shortest. You can see that this bridge has 2, this bridge has 2, and this bridge has 1. Well, 2 is longer than 1, but these 2 are the same length, so it doesn't matter which one I put. Okay, they're 2 and 2. Okay, so that's why I have 2, 2, and 1, right? Inside my square brackets, I put 2, 2, 1. Whereas if you look at this compound here, if I highlight the bridgehead carbons in yellow, like this, okay, you can see that one bridge has 1, 2, 3 carbons. This one has 1, and this one has 1. It's got a total of 7 carbons, but we say bicyclo 3, 1, 1. So going from from largest to smallest bridge, like that. Okay, so give me a thumbs up if you're even like 50% of the way with me on that, because you're going to have to try it yourself. Okay, now I want to show you one more thing before I expose you to it, is what if you have something like this, okay, where you have something that looks like this. Okay, you might like, well, how is that a bicyclic compound? Well, there's 2 rings. There's 2 4-membered rings attached to each other, right? So this would be this would be a bridgehead, and this would be a bridgehead. The total number of carbons is 1, 2, 3, 4, 5, 6. So this is some kind of bicycloheptane. So we would say bicyclo, open bracket, close bracket, heptane, hexane, 6 carbons. But if I count the bridges, okay, you see the 2 bridgehead carbons are highlighted in yellow? Well, where are my bridges? 1, 2 carbons. Why does it keep doing that? There's 1, 2 carbons here, 1, 2 carbons here, and there's no carbons in here in this bridge. So it's going to be 2, 2, 0. So we would put 2, 2, 0. Maybe it's because it doesn't have enough charge. Plug it in. Plug it in, plug it in. There we go. All right. So hopefully that makes some sense. So now, if we wanted to name these two compounds here, I'll highlight my two bridgehead carbons. There's one here and there's one here. Okay. So if I highlight this portion in yellow and this portion in green, which side should I number first? The yellow side or the green side? What was the rule? Think about all the rules we've learned. Do we go with the longest chain or the shortest chain, do you think? Exactly. I'm going to start numbering on the yellow side. Okay, good. So now that we have that established, if I highlight this one in green, those are the two bridgeheads. We've agreed that I should go on this side. Should I start numbering from where the yellow highlighter is or the green highlighter? Which one of those should be carbon number 1? Should it be the one in yellow or the one in green? It should be the one in green, shouldn't it, right? Exactly, because if I start numbering at the one in green, then I have 1, 2, whereas if I started numbering at the one in yellow, I'd have 1, 2. Well, if I go to this one, I only have one substituent at carbon number 2, whereas this way I have 2 substituents, right? So I want to give the second substituent the lowest possible number. So I start numbering like I have it in black. So I go 1, 2, 3. I'll use my black pen. 3, 4, 5, 6. And then for this bridge, I'm going to start here 7 because I want to give this methyl the lowest possible number. 7, 8. So it's some kind of bicyclooctane. So I'm going to put here bicyclo, open bracket, close bracket, octane. Now, what are the length of my bridges? This bridge has a total of 4 carbons. This bridge has a total of 2 carbons. We'll put 2 here. And then here, there's no carbons in the bridge, so I'll put 0. So we have bicyclo 4,2,0-octane. Now I just have to number the methyl groups. So I'm going to put 2, 2, 5, 7. So I'll put 2, 2, 5, 7 tetra methyl, and then the rest of the name. Bicyclo 4,2,0-octane. Like that. So 2257 tetramethyl bicyclo 4,2,0-octane. Seems like a mouthful, but if you just follow it step by step, it's not too bad. Now, in the next one, we have a total of, well, let's label our bridgehead carbons. We have one here and one here. Okay? Every bridge has 2 carbons in it. This one has 2 carbons. This is 2. This is 2. And there's a total of 6, 7, 8 carbons. So this is some kind of bicyclo 2,2,2-octane. So a bicyclo 2,2,2-octane. All right. So if we have bicyclo 2,2,2-octane, so I'm going to put here bicyclo 2,2,2-octane. Well, if I highlight one of those carbons in yellow and one in green, which one do you think I should start numbering at? The one in yellow or the one in green? And it's not a trick question. We want to give those 2 methyl groups the lowest possible number. So I'm going to start on the one that is in yellow. Exactly. So I'm going to start numbering here. 1, 2, 3, 4, 5, 6, 7, 8. So I have 2, 2 dimethyl bicyclo 2,2,2-octane. And there you go. So now you know how to name a bicyclic compound. All right. I thought I had another thing in here about bicyclics, but I guess that covers everything.
Cocaine would hop up. It
Sorry,
was fake, man. He wasn't really that angry.
My game froze, and I just had to.
Hello? Samuel, did you have a question? Okay,
No, I didn't. Sorry, my power went out and it just came back. I think
Okay.
my mic just turned on accidentally.
All right, no problem. All right, cool. So there you go. Now again, are you going to be able to name every bicyclic compound in the book just by doing this? No, you're going to have to practice it. But once you try it a couple times, students usually get the hang of it pretty quickly on naming bicyclic compounds. Usually the final exam asks you to name one bicyclic compound. If you're interested in exams like MCAT or DAT, they always ask a couple of bicyclic questions. How do you name a bicyclic compound? So it's really important that organic chemists learn the rules at least once of how to name a bicyclic compound. Real classic. So the next few sections are pretty short. You guys know what isomers are. It's compounds that are different structures but have the same molecular formula. So if I look at these two compounds down here, you can see that both are C6H14, but they're different compounds, aren't they, right? This one is hexane, and this one is 2-methylpentane. 2-methylpentane. So you can tell that they're different compounds one of two ways. Number one, you can see they have different structures. And number two, you can see they have different names. So you don't even have to see the compound. If they have different names, they're different compounds. So constitutional isomers are compounds that have the same connectivity of atoms, but they're not identical. Okay, and we're going to talk a lot about constitutional isomers as the class moves on. But the bottom line is, if you have constitutional isomers, they have the same molecular formula. So isomers, different structures with same molecular formula. Constitutional isomers have a different connectivity of atoms. So check this out. It says here that as the number of carbon atoms increases, the number of constitutional isomers increases. So if you go from 3 carbons, there's only one possible way to arrange it. If you have 4, there's 2. If you go to 5, there's 3. 6, there's 5. Then you go up to 9 carbons, there's 35. 10, there's 75. I have it written down in my notes somewhere. But if you have, let's say, 20 carbons, there's 366,000 ways or something. So you can see how it goes off the charts really quickly. There's no formula that you can use to predict the number of constitutional isomers. There's no easy way to calculate it. But the idea is, as soon as you get up to, not that many carbons, you start to have so many isomers that it gets very difficult to keep track of them all. Now, if you're wondering about constitutional isomers and you're having difficulty recognizing whether two compounds are identical or are different, there's 2 ways you can do it, okay? So if you look at these compounds on here, these are C6H14, okay? If you look at the first one, let me use my red pen. This one is hexane. This one is 2-methylpentane. This one here is 3-methylpentane. 3-methylpentane. This one here is 2,2-dimethylbutane, and this one here is 2,3-dimethylbutane. Okay. Now, if you look at the 2 that are highlighted in green, you might say, well, those are 2 different compounds. They're actually identical. Okay. There's 2 ways to figure that out. One way is to flip the molecules around, and then you can see that they're identical because remember, you have free rotation around sigma bonds. So you can rotate this bond, and that would give you something that would look more like this. Okay. Like this. And then maybe it's easier to see that this and this are identical. But if you're having difficulty flipping them, you could also name them. Okay. And you can clearly see that the name of this compound is also 3-methylpentane. So again, there's 2 ways. Number one is to manipulate it in your mind. Just manipulate them around and say, okay, well, these are identical. They have the same connectivity, so they are the same. Or if you can't do that, then you just name them. If the names are identical, they are the same compound. So you have 2 ways of doing it. So again, if you take a look at those 2 compounds that were on that previous slide, again, if you just rotate this bond, son of a gun, if you rotate this bond 180 degrees, you would end up with this, okay? It's going to look like this. And then it's easier to see that these 2 are identical. Or if that doesn't work, you can just name them and see that they're both 3-methylpentane. Okay, either way works. but I recommend trying both. I recommend manipulating everything, in your brain because it's good to be able to do that. But I also recommend practicing your nomenclature. All right. Relative stability of isomeric alkanes. Well, if you take a look at these compounds, you see that these are all C8H18. Okay, so they all have the same molecular formula, but they all have different names, don't they? So let's practice naming them. The first one is octane. The second one, 1, 2, 3, 4, 5, 6, is 2,5 dimethyl hexane. And the next one is 2,2,3,3 tetramethylbutane. So 2,2,3,3 tetramethylbutane. So they all have the same molecular formula. So they're isomers, but they're constitutional isomers because they all have a different connectivity, right? They all have a different name. Now this is where it gets really interesting. Take a look at these. If there's a funny way to summarize this, which is organic chemists learn a lot about organic compounds by burning them. Okay, so these are all hydrocarbons, right? They're all just made of carbon and hydrogen. So if you burn them, okay, you end up with the same products every time. You end up with 8 carbon dioxides and 9 waters. But if you look at the amount of heat released, you notice that octane releases the most heat. And then the last one, the 2,2,3,3 tetramethylbutane, releases the least. So what does that mean? It means that the 2,2,3,3 tetramethylbutane is the most stable of all of these isomers. So our conclusion is the more branching you have on your alkane, the more stable it becomes. Okay, so write this down because this is not written in my slides, but I want you to know this. More branching equals more stable. Now, the explanation as to why that is not covered in our textbook at all. It's not even mentioned, okay? It's based off of something called proto-branching, which is way beyond, way beyond the scope of our course. So you don't have to know it at all. All you have to memorize really is that the more branching you have, the more stable the compound becomes. And so when you buy gasoline and you see octane on it, what you're paying for is more branched hydrocarbons. But anyhow, I digress. I'm not going to ask you about that. So section 4.5, for some students, they just think it's the most interesting thing of all is studying the sources and uses of alkanes. But I'll just be honest with you guys. It is fun to read about it. I'm interested in it too. Trust me, I like reading this part, but we don't test you on it, okay? We don't test you on it. It's not in the MCAT. It's not in the ACS. It's not in any of those exams. So there's already enough content in the class. But again, it is kind of a fun FYI if you want to take a look at it. I think that one of the most interesting things in this is that it doesn't go into detail on this slide. Let me see here. Yeah, it talks about gasoline here. So let me just show you. When they take crude oil and they distill it fractionally, so they take the lowest boiling fractions off first, those are used for natural gas. Then beyond that, we have solvents like pentane and hexane. After that, once you get into 5 to 12 carbons, this is where the money is, right? Because this is where you can make gasoline. Now, if you're like, well, I thought that gasoline was made out of compounds that only are comprised of 8 carbons. Well, hold the phone. We'll get to that in a second. Above that, we have higher boiling. So we have things like kerosene. And then above that, you have things that are even higher boiling, like diesel fuel. And then up to that, you get into things like asphalt and greases and stuff like that. But going back to the idea of gasoline, right? So it turns out that gasoline is actually a mixture of straight, branched, and aromatic hydrocarbons, but they're in this range of 5 to 12 carbons. Now, when they distill crude oil to get gasoline, it turns out that this fraction is only about 20%. Okay, so there's only about 20% gasoline in there. But what they do is they break down larger alkanes into smaller molecules. You can see that this one has 1, 2, 3, 4, 5, 6, 7. So that could be used in gasoline. And this one has 5 carbons. And so we break them down into smaller molecules, and then they can be reformed into branched alkanes. And so the idea is that they can take gasoline and take it from 20% to about 50%. Take crude oil and convert it from about 20% gasoline to roughly, it says 47%, but whatever, close to half of it. So that's the processes of cracking and reforming. Again, I'm not going to test you on this one bit, so don't worry about being tested on it, but it is kind of fun to read about. All right, the last section I want to cover with you today, it's getting pretty late in the day here, is the idea of a Newman projection. And before next class, I want you to be sure to read the remainder of the chapter, but I want to introduce you to the idea of a Newman projection before you start reading that portion. So if we take a look at the three-dimensional molecule of ethane, right? This is CH3, CH3. It's just an ethane molecule. You can see it's drawn here in 3 dimensions. Well, if you twist it slightly and then tip it up, you can get a sawhorse. We call this a sawhorse representation. And then the last one is if you look straight down, this is an eyeball. If you look straight down this carbon-carbon bond, maybe I'll highlight it in blue. Okay, then when you do that, you get what's called a Newman projection. And Newman projections are really useful for comparing the relative stability of conformations of a compound. So what you have to do to see a Newman projection is look down a particular carbon-carbon bond. So you can see the human eyeball here looking down it. And the carbon in the front, we represent that as a dot, okay, or just the point intersection of 3 lines. The carbon that's in the back, the one I'm going to highlight in blue, that is represented as this circle here. So again, you're like, well, the carbon in the back, shouldn't it be smaller? Well, it's not the way it's drawn, okay? The way the carbon in the back is drawn is with a big circle, and the point of the intersection of the 3 lines in the front, that red dot, that represents the front carbon. Now I'm going to take a chance here and go to my camera. And I did this with you this morning before I started recording. If you remember, I started showing you a Newman projection. Where the heck is my camera? Okay, so stop presenting. There we go. It takes me a while to go back and forth. Can everybody see my camera? You guys see me? Yeah? Okay. I can't see myself. There we go. Okay, thanks. Thanks, you guys. Okay, so this is the molecule of ethane right here. I know you can make them with a ball and stick model, but this is actually easier for me to show you. So these are the 2 carbons. You have 1, 2, 3 hydrogens here and 1, 2, 3 hydrogens here. So CH3 and CH3. Now, if you turn it like this, let me make sure it's perfectly staggered. So if I turn it like this, kind of like that, that is your wedge or your sawhorse projection like this. But if you turn it completely 180 degrees, that is a Newman projection, okay? Your eyeball is looking down here from here to here, okay? So there you go. So now what we're going to cover is that we know that there's free rotation around a carbon-carbon bond. You can see how easily these turn. So if you look down that carbon-carbon bond and everything is as far apart as possible, so if we take 360 degrees divided by 1, 2, 3, 4, 5, 6 angles, you get 60 degrees. So that means that this angle here is 60 degrees. Okay, we call this the staggered conformation. If I rotate it 60 degrees, then everything is being blocked out, and we call that an eclipsed conformation. And the eclipsed conformation is high in energy, and then the staggered conformation is going to be lower in energy, right? Because we have less steric repulsions. So there you go. So that's a Newman projection. Again, we have our wedge and dash like this, if you can see it. Okay, there's our wedge and dash. Then you turn it and you get a sawhorse, and then you turn it all the way and you get your Newman projection, which can be staggered, which is lower energy. And then if you turn it 60 degrees, it becomes eclipsed, and that's going to be higher in energy. So if you keep rotating it, you go from low energy to high energy. This is me trying to act it out for low energy to high energy, so on and so forth. Everybody with me on that idea? This is, again, eclipsed. Cool, awesome. I'll go back to my slide so you don't have to look at deal with that anymore, but hopefully that's helpful for somebody. And that's how a Newman projection works. Now, ethane, and again, I'm not making light of ethane, but ethane is the simplest possible molecule that you could look at a Newman projection of. So if we take a look at this example, now this is something that you're going to have to practice. I know I say that all the time, but if I look at the carbon in the front, okay, that's this, I'll use the red again. The carbon in the front is this one, okay? What is the viewer seeing? Well, there's two hydrogens here that aren't shown, right? There's one going in the back and there's one going in front. Why do I know that? Because this carbon is sp3, so it's tetrahedral. So what does the viewer see? The viewer sees going straight down, right? There's a methyl group, and then there's two hydrogens. There's one going to the left and one going to the right. So if this is the whole person, okay? So if this is the person and they're standing up like this, okay? Or they're laying down or whatever, okay? And they're, okay, there you go. Perfect. If you have, hold on, they're studying organic chemistry, so they're smiling, okay? If the person is looking down in that direction, okay? If I label this as HA and this is HB, okay? So there are these two protons. Could anybody tell me which one is HA? Would it be the one on the left in the blue circle or the one on the right in the blue circle? Which one would be HA based off of the way the person sees it? Thanks, Rubio. It's the one on the left, isn't it? Exactly. This one would be HA and this one would be HB, right? Okay. Now, what's the person seeing in the back? In the back, the chlorine is going straight up because all of this is in the plane, right? This is what's in the plane of the viewer. And then we have a methyl group, which is on the same side as HA, our CH3 group. Okay. And then we know that there's also a proton that's not drawn, okay, but it's there. We could call that HC if you want to, which is on the same side as HB. Now, again, if you can't see what I'm drawing here, then you might have to get a handheld model out to help you with that. But that is how you look at a Newman projection. So what I would like you to try before lecture on Thursday is to try to draw the Newman projections of both of these. But I'm going to get you started on just the first one, okay? So if we look at just the first one, if we put a red dot on this carbon, okay, it's going to be like this, and that's where there's going to be the intersection of three lines. Now we see there's something going straight down, so we'll draw a line going straight down, and that means we're going to have something coming up here and something coming up here. What are those two other things? Well, we've got the CH3 group going down like this, then we have a chlorine, and we also have a hydrogen. I want you to try to figure out which side is the chlorine and which side is the hydrogen. The carbon in the back is the blue dot here. I'll just put a circle like this. Just forgive me here. So I'm going to erase these two so we don't get confused. Then I've got something going straight up in the back. Okay. Son of a gun. Got something going straight up in the back. I'll use my blue pen. Okay. Then we have something going down this way. And we have something going down this way. So I want you to figure out, is this chlorine on this side or this side? And is this chlorine on this side or this side? I know that a lot of you, probably all of you know the answer right away, but I want you to try it first, okay? We've covered a lot of content today. And then once you get that one, I want you to try this one as well, but I want you to try to draw the Newman projection. So draw, you're going to have something like this. Here I said I want you to do it, and then I'm doing it for you, and you didn't even ask. So anyhow, you have something like this, okay? And then we have our circle in the back, and we're going to have something here, and something here. I want you to see if you can fill those in before class on Thursday. After that, once we're done with Newman projections, we're going to get into what's called conformational analysis, which will involve a little bit of me going back and forth in between the slides and me just acting it out with my model, so to speak. And so be sure to read this section about staggered and eclipsed, and then the conformational analysis of ethane, propane, and butane. And also be sure to read the section on cyclohexane. So there's a huge section on cyclohexane, so be sure to read that too, and we'll finish that on Thursday. All right.